Hello everyone, my name is Joseph. I'll be going over problem 4.21 from Griffiths EM. The problem says, a certain coaxial cable consists of a copper wire radius A surrounded by a concentric copper tube of inner radius C. The space between is partially filled from B out to C with material of dielectric constant epsilon R as shown. Find the capacitance per unit length of this cable. Regular capacitance is C over V, and so then capacity per unit length is C over L, and we multiply both sides by 1 over L. We will assume for some length L we have some charge Q, and that's okay because for capacitor, the capacitance is a property that only depends on the geometry of our capacitor. So the charge should drop out of our final answer. So with that out of the way, we need to find the electric potential difference between our capacitor plates, which I am calling V. And in this case, it's just a potential difference between the potential at A minus the potential at C. So the potential difference is the path integral of minus E dot dl. But before we can calculate this integral, we need to find what E is. But finding the electric field directly is a complicated monster, because here we have vacuum and here we have a dielectric, and in the presence of an electric field, the dielectric picks up a polarization, and the polarization affects the electric field, which affects the polarization. So the solution is to find the electric displacement, which is way simpler, and we can find E with this simple linear relationship. This chapter is on linear dielectric, so we are assuming our dielectric is linear. So I am using a cylindrical Gaussian surface, which will make the problems a lot easier. Now, the next natural question is, in what direction is the D? And it turns out, due to cylindrical symmetry, D points in the s-hat direction. You may ask, why is there no z component of the D, and why is there no phi component for D? Well, assume there is a z component and a phi component for D. You can take your cable and rotate it. And just by rotating it, you have completely changed the direction of your D. But your cable is physically identical to how it previously was. So the problem with this is any other observer, they could have just as easily said that the z components go this way and they point this way. And then when they flip the cable, now your z and phi components are pointing in a completely different direction. Both observers are contradicting each other. So the conclusion is that there must be no z and phi components of the electric displacement D. The other question is this D constant? Assume there was a phi and z dependency. So let's start by tackling the phi dependency. If there was a phi dependency, say here you started with some initial D naught, and it got stronger as you went along the cylinder, so it's stronger over here. Well, you could also just as easily rotate your entire cable, and just by rotating your cable, you increased D. But by rotating the cable, you're left with the same cable as before. You come into the same contradiction as before. So the conclusion is there is no phi dependency. What about Z? If D did get stronger as you moved along the Z-axis, well, someone else could have just as easily shifted their axis, or you could just walk along the cable and you can increase D's strength by walking along the cable. But you come across the same contradictions. You're left with the same cable as before. So the conclusion is there must be no Z dependency. So D is constant along our Gaussian surface at constant radius S, and it points in the s-hat direction. So to find D, we can use the electric displacement version of Gauss's law, which says D dot dA is equal to the free charge enclosed. So starting with S less than A, we are inside our conductor, and our Gaussian surface is inside the conductor. And for these problems, especially chapter 4, we're assuming electrostatic conditions. So that means all the charges are hanging out on the boundary of the conductor. Our free charge enclosed is 0, and that just tells us that our D is 0 inside our conductor. For S in between A and C, we are now enclosing the inner copper tube, but we're still inside the bigger copper tube. So the only charge we're enclosed is the charge on the inner copper tube. So this is just Q, as we have assumed before, for some length L. Now moving on to calculating the flux integral. So I can split the Gaussian surface into its three surfaces, the ends, and the perimeter of the cylinder. Our n hat points in the z direction, this one points in the minus z hat direction, but it doesn't matter because our d points in the s hat direction, and s dot z hat is going to be 0. So we get no contribution from surface 1 or surface 2, and all of it comes from the outer surface, or the sides of the cylinder. The side of the cylinder points in the s hat direction, so our flux integral becomes d dot dA. D is constant, so I can pull it out of the integral, and I'm simply left with the integral of the surface, which is just the area of the outside, which is just 2 pi SL. Solving for d, I get d as q over 2 pi SL. Lastly, moving on to s greater than c, our Gaussian surface is now enclosing the entirety of the coaxial cable, so we are enclosing both charges here and here, so our total charge enclosed, free charge enclosed, is 0, telling us that our d is 0. So in summary, we have that our d is q over 2 pi SL s hat in the s hat direction in between a and c, and 0 elsewhere. Now, since we know that E is related to D by a factor of 1 over epsilon r and epsilon naught, and this came from this equation, we can solve for E. We have to be careful about this because we have epsilon r in the equation, and that depends on what region we're talking. So I split the region A to C in between the two regions, the vacuum region, which is A to B, and the dielectric region, which is B to C. In vacuum, ER is 1, so it doesn't show up. In dielectric, we are given epsilon r, so it shows up there. And so now we have found E. So the potential difference is minus the integral of E dot dl from C to A, and I can split this path integral. Instead of having it go from C to A, I can have it go from C to B and B to A. And we do this because E is different for these two regions. We take our solved electric field and plug it in for those two different regions, and we note that now it's just simple integration. This integral has several constants, q, 2 pi L, which I pulled out and threw them over here. This integral has q, 2 pi epsilon naught, epsilon r, L as constants, which I pulled out. And we're left with the integral of 1 over s, which we know is just ln of s. Both integrals have q, 2 pi epsilon naught, and L as constants, which I pulled out. And after iterating and using properties of natural log, we're left with ln of c over b plus 1 over epsilon r times ln of b over a. And this is our potential difference V. So now I go back to my capacitance per unit length and plug in my V. Notice how our L cancels out, our Q cancels out like I mentioned earlier, and we're left with 2 pi epsilon naught all over ln of c over b plus 1 over epsilon r times ln of b over a. Thank you.